Hey team, I'm Maddie. Welcome to Science Side Up, and today we're talking about hydrostatic balance. Broadly speaking, a system is in hydrostatic balance if the pressure gradient force is exactly balanced by gravity. Let's think about this in terms of a balloon in our atmosphere. If this is the ground and this is our balloon, then we understand that the force of gravity is acting to pull the balloon down. Fg, force of gravity. But if this balloon isn't moving, if it's just hovering right here, I know that's not how most balloons work, but bear with me, think about it with me. If this balloon is neutrally buoyant with its surroundings, then what force is going to be acting to pull it up to exactly balance gravity? Well, that's going to be what's called our pressure gradient force, usually denoted as PGF. We know that pressure in the atmosphere decreases as we go up, so there's a change in pressure along the vertical axis. A change in pressure across a distance, right? As we go up, pressure goes down. That creates a pressure gradient, and it turns out that a pressure gradient is going to have units of force. So anytime you have a change in pressure over some distance, here we're thinking vertically, but this can certainly happen horizontally as well, that's going to cause fluid to want to move. It's a force that's going to make it want to move. In this case, the pressure gradient force is exactly balanced by the force of gravity. If our balloon was lower, then the force of the pressure gradient force would be greater than the force of gravity, and it would make our balloon move up until it was in that neutrally buoyant state where it doesn't want to move up or down. Similarly, if we tried to pull this guy up a bit, now the pressure gradient force up here is weaker than the force of gravity, so gravity would pull the balloon back down to the point where it's neutrally buoyant. So this gives us a relationship between the change of pressure with height and gravity. So specifically that looks like this. The change in pressure with respect to height is equal to negative density of the air times gravity. This negative corrects for the fact that as height goes up, pressure goes down. For anyone in the audience who has had calculus, yes, this is the partial derivative of pressure with respect to height. But if you haven't had calculus, don't worry about that too much. The concept is change in pressure with respect to a change in height. So this is all well and good, but why is it something that we want to know about, or why is this an equation that we want when we're talking about weather stuff? Well, one, if we're thinking about climate timescales, so timescales of decades and longer, and we're thinking about how the atmosphere behaves over those very long timescales, the atmosphere is approximately in hydrostatic balance across those timescales. So that helps us simplify some of our math and reduce computational expense for our climate models and things like that. Another thing hydrostatic balance gives us is it gives us an equation for how pressure and height relate to each other. If you remember a few videos back, I said that pressure cuts in half for about every 5 or 6 kilometers you go up. Well, what's great is now we could precisely solve for pressure as a function of height and, solve for that everywhere instead of going by a rule of thumb. And another thing this equation lets us do is for all of our systems of equations for understanding the atmosphere, it's going to let us replace z, height above the ground, as our vertical coordinate with p, pressure. Oftentimes in meteorology and atmospheric science, pressure is the more useful vertical coordinate than actual height. Why, do you ask? Excellent question. Consider a mountain. both Timmy and Susie are standing on the ground. Their z coordinate, their vertical height above the ground, is 0 for both of them. But there's clearly very different things going on between Timmy here at, say, sea level and Susie up on top of a mountain. But the pressure at the surface of those two locations will be very different. For Timmy, let's say it's about 1,000 hectopascal, and for Susie, maybe it's 750. So if we use pressure as our vertical coordinate instead of height, we actually get a lot more information, and it removes some of the complications of terrain effects for us. Okay team, that's all I've got for you today. I hope you liked this video, and I will see you all in the next one. Bye team!